In this last video, which is actually going to be pretty short, we're going to talk about some other kinds of substitution reactions of benzenes that don't go by electrophilic aromatic substitution. So there's other mechanisms that could take place. One is nucleophilic aromatic substitution, and the other one is called elimination addition, otherwise known as benzyne chemistry. So in the first sort, some of these examples don't really look like they make sense, right? Because what we've been talking about up to this point is really strong electrophiles when we treat benzene with really strong electrophiles. What this reaction looks like is we have a really strong base and a really strong nucleophile, right? Hydroxide, as we know, is a good nucleophile and a strong base. This almost looks like an SN2 reaction, but remember, we know SN2 reactions can't take place on sp2 hybridized carbons, right? So something else must be going on. Maybe this nitro group has something to do with it, which makes sense, right? Because when it's in the para position, then this reaction readily occurs at 70 degrees. But when it's in the meta position, nothing happens, right? So what's going on? How's this reaction working? This is a substitution to create a phenol, which is an alcohol group on an aromatic ring. We're replacing a good leaving group with an alcohol using hydroxide. So let's talk about the mechanism here. So this is taking place by a mechanism called nucleophilic aromatic substitution, or substitution nucleophilic aromatic. If we look at the first example that we showed on the last slide, hydroxide is a good nucleophile. What you must have for nucleophilic aromatic substitution is a good leaving group and a very strong electron withdrawing group in the para or the ortho positions, or both. Because what's going to happen is hydroxide is going to add to the same carbon where bromine is via nucleophilic attack, which is then going to create a stabilized carbanion, right? So remember, nitro groups are very destabilizing when you put a positive charge, but if you put a negative charge next to a nitro group, that's going to help stabilize that negative charge. So now we have, instead of having a carbocation intermediate, we have a carbanion intermediate. So putting that negative charge at the same position where the nitro group is going to be really stabilizing. And then what can happen is, if we have a good leaving group here, then we can restore aromaticity by kicking out the bromide to give us our product that's shown. So this makes sense, right, that this would only happen in cases where we have a nitro group in the ortho-para position, because if it was in the meta position, there's no way that we could generate a stabilized negative charge. So let's say we look at the example that the other example that was on the slide, right? If we have this guy and we attack it with hydroxide, we form a negative charge here and here and here, which I'll show. So we have a bromide and a nitro group, and we have these double bonds, and we have this guy, right? And we have a negative charge here, which is not stabilized. A resonance structure would put a negative charge here, which would not be stabilized, and a resonance structure would put a negative charge here, which would not be stabilized. So this doesn't happen because it's too high in energy. So the only time you can get nucleophilic aromatic substitution is when you can form stabilized negative charges next to nitro groups. Okay, but what if we heat the living crap out of this reaction? So if we just mildly heat the reaction without a nitro group, we just said nothing's happened, 70 degrees, nothing happens, we don't have any nitro groups. If we heat it to 350 degrees, though, we do get a phenol. So is this happening by SN2 reaction, maybe? No, that can never happen. And even in this case, we can actually use pretty low temperatures, but now we have a very much stronger base, which is NH2 minus. So in this case, we're not seeing, this is not nucleophilic aromatic substitution, and it's not SN2 reaction. And if we get additional information, it will help us figure out what the mechanism is. So let's say we take the same compound, except we put a methyl group here. So if we have a CH3 para to the leaving group, what we notice is that we get a mixture of compounds. One where the nucleophile added para, and one where the nucleophile is meta, which is weird because how could the nucleophile add to this carbon, which is meta to the methyl group, if the leaving group is on a different carbon? Similarly, if we label the carbon, so let's say we make this a carbon 13 isotope, which is what the star means, then if under the same conditions we notice that there's a scrambling of the isotope, half of the time the isotope is on the carbon where the leaving group was, but half the time the nucleophile is one carbon away. So to explain this observation, we need to propose a new mechanism, and that goes through a very high energy intermediate called benzyne. Okay, so let's talk about the mechanism of what's going on here. So let's look at the example that we gave at the end of the previous slide, right? We have chlorobenzene, and we've labeled this carbon somehow with an isotopic label so we can follow the carbon through the reaction. Now we treat it with a really, really strong base, like the amide ion. What happens actually is an E2 reaction initially. So we deprotonate this hydrogen, which is next to the chlorine, with this really strong base. We form a pi bond, and the chloride gets kicked out. And what we have here is an extremely high energy intermediate, which is called benzyne. And notice one of the two carbons in benzyne is labeled, but in the absence of that isotopic label, we would have a mirror plane here, and these two carbons have the same reactivity, right? And it turns out because benzyne is really, really strained, you can't really have a carbon-carbon triple bond in a six-membered ring, so it actually looks more like a diradical, where you have an electron here and an electron here, and a resonance structure of that kind of a deal is where you have one carbon with a lone pair of electrons and one carbon with a positive charge. So what you see is electrophilic character on one carbon and nucleophilic character on the other carbon. So if we have an excess of this amide ion in the presence of benzyne, then what happens is after elimination, the way you want to think about benzyne is that it's a really, really strong electrophile, right, because of the strain, and so the amide can attack either this carbon or this carbon, and there's a 50% likelihood. So half the time we get NH2 here and a negative charge, and half the time we get NH2 here and a negative charge here, and then these can undergo proton transfer from ammonia, which was the solvent, to pick up that remaining hydrogen to form the product. And notice that 50% of the time this carbon is going to be labeled and 50% of the time this carbon is going to be labeled. And so this is basically a mechanism that explains why we see that 50-50 mix in terms of that labeled carbon. Benzyne is also a really powerful dienophile, and we can use it to form these really cool Diels-Alder products that have an aromatic ring. So remember, this is the two carbons of our Diels-Alder dienophile, and these are the four carbons of our diene, and so we get a carbons 1 and 2 bonded to carbons 1, 2, 3, and 4. So to summarize, I just want you to be familiar with these two alternative mechanisms for substitution on benzene-containing compounds. One is nucleophilic aromatic substitution, and one is an elimination to generate benzyne and addition to benzyne to generate a new product.